Good morning, everyone. My name is Philipp Moll. I'm from University Klagenfurt. Together with my colleagues, Sebastian Theuermann and Hermann Hellwagner also from University of Klagenfurt, and with Jeff Burke, we are working on bringing ICN to online gaming. And in this work, titled Distributing the Game State of Online Games towards an NDN version of Gamecraft, of Minecraft, we analyzed state-of-the-art online games, looked how the network stack of those games work, and propose a system to bring ICN to online gaming. So the first part of my presentation is why we want to do it, and yeah, let's start with the motivation. So when you look at current online games, you will see that current games rely on really state-of-the-art and latest technology regarding computer graphics. But when you look at the network stack, you will see that most games rely on decades-old technologies which were never intended to be used for gaming. And this, in some cases, results in a lot of overhead. For instance, a lot of traffic needs to be sent redundantly to all clients playing the game. And we think that named data networking could be better suited for games because, for instance, named data networking has inherent multicast functionality, which could reduce or eliminate redundantly sent traffic. Also, named data networking allows to separate the game state information from the server simulating the game, which allows for easier scalability or error recovery, but also NDN brings packet level security, which increases the overall security of games. So for all those who are not familiar with NDN, I want to give a very brief introduction into NDN and explain what it basically is. Basically, NDN is a novel internet architecture and a promising candidate for future internet architecture. NDN has a strong focus on content, which means if you request data in NDN, you don't request data from a specific host, but you issue an interest for a system-wide unique name identifying the data. And NDN is a strong pool-based system, which means every piece of data which is sent over NDN has to be requested first. And NDN has some additional very useful features, such as inherent multicast and multipath support, but also client-side flow control, and NDN has a strong focus on security. So the basic principle of NDN is quite simple. There are two types of packets, namely interest packets, which are used for requesting data with the name specified in the content link field. And there are data packets which then actually deliver the requested data. When requesting data, the first step is to issue an interest containing the name of the requested data. The interest is then sent to the network where it's forwarded based on its name until it meets a node which has a copy of the data available, and the data then flows back in the reverse path of the interest, which is possible because interests leave kind of breadcrumbs on each forwarding nodes, which are realized by entries in the so-called pending interest table. So I think that's sufficient background about NDN, which is needed to understand the rest of my presentation. Now I want to focus on online games and how online games basically work. Therefore, so for our work, we decided to use Minecraft as a representative for online games because Minecraft contains all elements of current massive multiplayer online games, which is the game genre we are focusing on. And basically, Minecraft is currently a very popular online game. Very popular means that in 2018, there were about 74 million active users of Minecraft per month, which means more than 70 million people played Minecraft in a single month, which is quite a lot, I would say. And also, Minecraft ranges among the top 20 games on Twitch, which is also not that bad. Minecraft has a single-player game mode, which is not that interesting for us, but also a multiplayer game mode, which is what we are focusing on. The game itself is closed source, but we can still use it for research because the developers of Minecraft are very permissive towards modifications, and they allow to everyone to run basic standard Minecraft server or a modified Minecraft server, which makes it very easy for us to manipulate the behavior of Minecraft and also to exchange the network stack. So when looking at games, there's basically the current state of the game needs to be represented by something, and in the case of games, this state is called the game state. And most games have two different types of game state data. The first thing is the data which makes up the structure of the world. In Minecraft, these are blocks as visualized here. And the second type of data making up the game state are dynamic objects which can walk around through the world, and those are entities. So in Minecraft, the whole world is built out of cubic blocks, and the blocks can be made of different materials, which give the world its colorful and distinctive look, which everyone knows from Minecraft. And for storage purposes, blocks are structured into sections, as visualized here. So 16 times 16 times 16 blocks make up a section, and 16 horizontally aligned sections then make up a chunk. And chunks are very important data structure in Minecraft because they are used to persisting the game world on the server, but also they are used to communicating the state of the world between server and client. So the other type of objects, as I already mentioned, are entities. They are more dynamic objects than blocks because they can move around in the world. There are basically three types of entities, namely block entities, which are just more dynamic blocks which allow for user interaction. Then there are living entities. Living entities are players and mobs. Those are the entities which can move around freely in the world and cause a lot of traffic. And there is a third type of entities, the non-living entities, which are items or projectiles which fly around in the world. They are also dynamic because they can move, but their behavior is defined by physics. So, for instance, an item can fall on the ground and lies there until it's picked up, or an arrow flies through the world until it hits another object and stays there. So, I think with this information, it's already possible to basically work with games, because now we know what the data behind games looks like. What we also did in order to improve the networking stack of online games was to look on how the game behaves over time. This is why we organized a Minecraft playing session with 4 players playing collaboratively playing Minecraft, and we gave the players a task which they need to perform, and this is very common behavior for collaborative Minecraft games. And we captured the network traffic of this gaming session, and we also traced the game state changes during this playing session. And yeah, basically, when capturing the network traffic or when analyzing the network traffic, we then looked into the packets, which data is in the packets, and we extracted information like entities, entity IDs, types of entities, or the locations of the entities in the game world, and also the actions they did and the time when the packets were sent. And our first observation from this multiplayer gaming session was that all the packets, or the content of the packets, is carrying the packets are carrying traffic which is only for a very small portion in the game world, as visualized here in these two graphics. And this was the first indication that because it's a 4-player game, 4 players played the game, this was the first indication that a lot of traffic is possibly redundantly sent to all the clients. And looking more deeply into the packets, we saw that that's really true. Basically, 62% of all traffic which was sent from the server to the clients was sent redundantly. And when using efficient multicasting systems like we have in NDN, we could reduce this redundantly amount of traffic. So then we further analyzed the network packets which were sent to the client, and we found that the dynamic behavior of the object can also be found in the packets. For instance, here we plotted the inter-packet interval, which means the interval between two packets which are carrying data for a specific entity. Here we plotted the inter-packet interval for player entities, and here for creatures which are running around in the world. And we see that the inter-packet interval is very low. It's 2 ticks between 2 and 3 ticks for players. 2 ticks is about 40 milliseconds. And for mobs, it's also quite low. It ranges between 3 and 20 ticks for most packets. This represents the behavior, basically, of the entities. Because players and mobs can basically change their behavior at any time. At any time when they change the behavior, the information needs to be sent from the server to the client. And this means that basically those entities have low latency demands. When looking at other objects like for items and projectiles, for instance, we see that the inter-packet interval is much higher, which is caused by the fact that their behavior is predefined by physics and can't change so often. Then we also traced the changes to the game state. I think for a matter of time, I can't spend too much time on this figure, but the most important facts we observed are summarized here. Basically, throughout the whole gaming session, we only had 4 player entities playing the game, but there were on average 250 concurrent entities in the game. And when thinking of how much data, how much packets those 250 entities produce, we already know that the networking part in NDN is going to be quite challenging. And also the game server simulated 500 chunks of the game world at any time during the game. But of those 500 chunks per second, on average, only 30 chunks changed, which means that the structure of the game world is quite static and doesn't change too often, because most of the chunks don't change. So we used then these insights to propose NDN-based gaming architecture, which I want to explain now. First, I want to give a brief overview about what a typical game server architecture looks like. Basically, online games usually have either one server or a full server cluster. In the case that there is a full server cluster, the game world is structured in different geographical areas, and each of the servers is responsible for simulating the game state of one of those map areas. But in order to simulate the map areas, the servers need a global view to the game state, and they have to exchange the game state information among the full server cluster, which is the first task we're doing with NDN. The first step is to distribute the game state information among a server cluster. And then in game architectures, there's also a client connected in IP-based games connected to a single server. And the client is controlling the player entity. Controlling the entity in games means that the client sends control commands to the server. The server then applies the control commands to the game state and sends the updated game state back to the client. So when using NDN, I already said the first step of us is to distribute the game state among the server cluster. When looking at Minecraft, we see that there's no distributed game server cluster in Minecraft. Minecraft is currently only a single server game, but our first step is basically to extend the single server game of Minecraft to a multi-server environment and then to synchronize the game state among this cluster. And in order to synchronize the game state, we plan to use a combination of NDN synchronization protocol and classical interest data exchange. We use the NDN sync protocol to notify the neighboring servers about which parts of the game state changed, and then classical interest data exchange to get the changed game state, to fetch the changed game state. Then the next step is then to connect clients to the server or to the server cluster using named data networking. So in the P-based games, it's basically only possible to connect the client to a single server. In NDN, it would be possible to not only connect the client to a single server, but to connect it to the full distributed game state, because by using NDN, it's not the game state or the distributed game state is not bound anymore to a specific server, but basically to a namespace. So for the client-server connection, we've got two different types of data. First, we have latency-tolerant data, which is the structural information of the game world, which only changes seldom. This is why we think that for the latency-tolerant server, online games can benefit from in-network caching and also from multicasting. And the second type of data we have is latency-critical game state data, which is mainly caused by entity movements and things like that. And if you think to this entity movement data, you have to think it could happen that the entity doesn't change for a long time, but if it starts walking around in the world, it will send a lot of consecutive packets regarding its changes. And therefore, we discussed the idea of notify and polling, where the game server notifies a client about the entity starting to move. Then the client can start polling the consecutive movement updates of the entity to basically get the entity changes. So this was now a short introduction or a short overview about our proposed NDN gaming architecture. Unfortunately, there's not much time left to discuss it in more detail. Before finishing my presentation, I want to draw a quick conclusion about what we did. We basically analyzed Minecraft's network traffic and game state changes. In this analysis, we saw that a large part of the traffic in the 4-player scenario, 62% of all client-bound packets were sent redundantly. And this is why we think that there's a high potential for NDN to be used as online gaming architecture. We proposed NDN-based architecture for gaming, which aims to reduce inefficiencies, but also which decouples the game state information from the simulating server. This, besides reducing inefficiencies, this also helps to build more scalable systems. Currently, we are in the middle of implementing this prototype. We just finished the multi-server or the inter-server game state synchronization. And as a last note from this work, the software artifacts which resulted from our work are of course open source and available on GitHub on this link. So now I want to handle the stage to those of you who are curious about our work and have some questions. Thank you.
Okay, thank you, the speaker. We have a few minutes for questions.
Thank you for the presentation. So, to use this game, does the consumer need to use NDN or?
Yeah, basically, in Minecraft, it's easy to manipulate this to change the behavior of the server, but it's more challenging to change the behavior of the client. But what we do is that we write a proxy application where the consumer connects to, and this proxy application then translates the original Minecraft traffic to NDN packets. And therefore, it's possible to use the standard Minecraft client, but the packets which are sent using NDN.
Even that is a configuration. You can reduce the traffic that much as.
Yeah, if the proxy is running on the client machine, the traffic is basically reduced between the server and the client machine.
Other questions? I can comment on the security aspects of original Minecraft and what you think NDN would bring for the security aspects.
Yeah, in original Minecraft, basically there's transport encryption used, and in this figure you see it. So I think what could be quite nice is when you think of this multi-server architecture, you could basically also add on something like an overlay layer over this multi-server architecture, which exchanges additional information, like for instance the number of servers in the cluster, or which server hosts simulates which region of the game world. But it could also be used to exchange something like key information, like which enables it then to encrypt the traffic which is sent between the servers with the keys which are exchanged in this overlay, and also it could be then used to share keys with client applications. So it's in Minecraft or in IP Minecraft, it's always the case that the single server is basically maintaining the whole game state of the world. And when then looking at NDN Minecraft, a lot of servers can, because the game state is not bound to the single server anymore, a lot of servers can then manage the game state in a distributed way, and each server can basically guarantee that, or verify that none of the other servers did anything which is not allowed. So I can see a lot of benefits, but maybe it's difficult to explain in that time frame.
We can talk offline.
Yeah.
So thanks again, the speaker.